Greetings, folks. You know what's going on with the work energy theorem. Net work equals the change in the kinetic energy. And you know how to do work calculations. You know how to deal with F dot D, and you know that if you have a conservative force that you know the potential energy function for, that the work that force field will do as a body goes from one point to another is equal to minus the change in the potential energy evaluated between the 2 points. What we're effectively going to do is to take all of that information, sort of put it all together and sort of rearrange things and come up with a relationship that's actually going to be very useful and very easy to use, which is called the modified conservation of energy relationship. Knowing how that relationship came into existence is going to be very useful to you in using it. And so that's what this video is about. It's basically the derivation of this modified conservation of energy relationship. So enjoy. We want to begin with the work energy theorem and note that the work net part of that relationship can be determined by figuring out how much work each of the individual forces does and then just adding those quantities up. So I'm going to assume that I've got 5 forces that are acting to change the kinetic energy of the system. I'm going to let force A and force B be conservative, and I'm going to assume we know their potential energy functions. What that means is if we want to know how much work A does, all we have to do is take minus the change in the potential energy function associated with A over the interval. Kindly notice the notation. The 1 is identifying point in time 1, which has to do with basically the beginning of the interval. The A is identifying the fact that this is the potential energy function associated with force A. The 2 is associated with point in time 2, which is to say at the end of the interval. Force C is assumed to be a conservative force that we don't know the potential energy function for, which means we have to use F dot D to be able to determine its work quantity. And I'm going to assume that forces D and E are non-conservative forces, like friction for instance, that don't even have potential energy functions defined for them. So to figure out how much work they do, we're going to have to use the F dot D approach in both cases. So if we write out the work energy theorem, the work that A does is equal to minus the change in its potential energy function. B is minus the change in its potential energy function. C is a dot product, D is a dot product, E is a dot product, and that's going to end up equaling the change in the kinetic energy. So now we're going to do a couple of things that are going to make things a little easier. First is we're going to distribute this negative sign. So the u sub 2a is going to become minus u sub 2a. And the negative negative is going to go positive, and we're going to end up with this. Similar thing here. And the second thing we're going to do is we're going to take the individual work quantities with the forces that don't have potential energy functions, and we're going to lump them all into one little bailiwick here, and we're going to call them the sum of the extraneous work that's done in the system over the interval. It's important to understand what the extraneous work is. It's effectively all of the work that's done on the system through the interval that hasn't been taken into consideration using potential energy functions. So here is that last relationship, and now it's time to do some rearranging. This is the kinetic energy of the system, the total kinetic energy of all the pieces in the system at the beginning of the interval. And it's got a negative sign out in front. I'm going to take that and I'm going to pull it over onto this side of the equation, and it's going to go positive. I'm going to leave all of the point in time 1 quantities on the left-hand side. I'm going to take all the point in time 2 quantities, which all have negative signs in front of them. I'm going to pull them all over onto the right-hand side, which is going to make them go positive. And I'm going to leave the extraneous work quantity exactly where it is. Once I get it into this form, you can see that here I have essentially all of the kinetic energy in the system as it exists at the beginning of the interval. Here I have what effectively is the sum of all of the potential energy quantities as they exist at the beginning of the interval. Here is all the kinetic energy at the end of the interval. Here is all the potential energy at the end of the interval. And here is the extraneous work that happens between when the interval started and when it ended. Writing that all out with summations yields this. And this is what is called the modified conservation of energy relationship. This is the bottom line of this video. This is the relationship that you're going to be using to problem solve. There are a few more things to be said. There are a couple of definitions to be had. There's a little bit of conceptual information to be given, which you're about to receive in the next couple of minutes. But this relationship is really going to be what's going to be important to you over the next couple of weeks. Having said that, you should probably know that the kinetic plus potential energy is sometimes lumped together in what is called the mechanical energy, the total mechanical energy of the system at a particular point in time. And that symbol is usually just E1. That's how it's characterized. So this modified conservation of energy relationship can be written as the total mechanical energy at point in time 1 plus the extraneous work that's happening over the interval will equal the total mechanical energy at point in time 2. This is just sort of a shorthand notation. This is why this is not as useful as is this. Again, this is what you're going to end up using in problem solving. This is something that's useful for discussion's sake. In this form, we can make a number of observations. The first is that if there is no, say for instance, friction and no other extraneous work being done over the interval, the total mechanical energy to start with and to end with will be the same, which means it won't change with time. When you have quantities in physics that don't change with time, they are said to be conserved. When you have a conserved situation, which is to say when the extraneous work is 0, you could start off with a certain amount of kinetic energy and a certain amount of potential energy, and their sum would give you the mechanical energy in the system. Those quantities don't have to stay the same throughout, though. The kinetic energy could go up, the potential energy could go down, and at the end of the interval, the kinetic and the potential energies could be different, but their sum would be the same. So the classical example of this is a body that falls from rest. It starts off with no kinetic energy and a whole lot of potential energy. Just before it hits the tabletop, it has no potential energy and all kinetic energy, but the net mechanical energy is going to end up being the same through the interval. Things get fun when you start having extraneous work happening in the system. So this is friction as an example. You start off with a certain amount of energy in the system, and as time proceeds through the interval, friction does work. It does negative work, which means it pulls energy out of the system, usually in the form of slowing the body down in ways that it wouldn't normally slow down. And by the time you get done at the end of the interval, the kinetic energy is less than it would normally be, which is to say that the total mechanical energy in the system is less than it would normally be. So you start with a certain amount of mechanical energy. You do negative work, you pull energy out of the system, you end up with less mechanical energy than you started with. The other side of the coin is a situation in which energy is put into the system via extraneous work. So here you start with a certain amount of energy. Maybe it's kinetic energy, maybe it's potential, but some mechanical energy. You do extraneous work in the form, in this case it's apparently there's a jetpack attached to the object that's putting energy into the system. And by the time you get done, the object is either gone higher than it normally would have, or it's moving faster than it normally would have. In some way, shape, or form, though, its final mechanical energy is greater than it started out with. And the reason why is because you've done positive work that's put energy into the system over the interval. Anyway, these last several points of amusement are just conceptual observations that are sort of interesting. I've also tried to get you into the mood of looking at systems from the perspective of energy content and putting energy into the system and taking energy out of the system. In any case, the real relationship that's important to you is the modified conservation of energy relationship, and you're going to be seeing a lot of that over the next few weeks. And that's it.